Hello everyone, my name is Niklas Hackelberg and I'll be showing you how we use Julia in our scanners for magnetic particle imaging, which is a new tomographic imaging modality. Generally speaking, medical imaging scanners use some physical principle to get a patient to emit some sort of signal, and then from this signal one can reconstruct a tomographic or a projection image of the inside of the patient. And these scanners are really diverse, distributed systems that need to coordinate a lot of different devices. And this coordination is the focus of this presentation. And while implementing our systems, we were faced with challenges that could be roughly grouped into two scenarios. The first scenario is what happens after and before a measurement. And here we need to get the scanner into a state where it can measure and leave the state again. And this usually involves a lot of different asynchronous tasks, such as moving a robot. But when we need to perform hundreds of measurements, it's really beneficial to intertwine this coordination, which can save hours of scanner time. And during the measurements themselves, we are operating under real-time requirements, especially for the signal handling. And here it's important to have a consistent high-performance data transmission so that none of the signal we actually want to receive is lost. The architecture of our systems can be seen here. We have a measurement computer that is running a Julia software stack with a graphical user interface, and this is using the MPI measurement package, which we wrote to control all the devices in our systems. And these devices can be roughly grouped into two sets according to their communication interface. The first group is a very heterogeneous group of devices that uses serial port communication. And for these devices we use the lib serial port package, which offers blocking I/O over serial port. And the second group is our send and receive cluster, which handles our signals. And this uses repeaters, which are low-cost specialized computers, which can each handle two input and two output signals. And for these we wrote an open source software stack called Repeater Data Acquisition Server. And this stack offers communication over TCP/IP and also includes the Julia client, which we use in MPI measurements to configure these devices and also to receive the samples they generate. And from Julia's threading capabilities, we are using a lot of the newer features, mainly the ability to spawn tasks on dedicated threads. And for task communication, we mainly use channels that pass around custom structs. Now, when MPI measurements wants to configure these repeaters, it's usually calling functions that look like this. So they all have a very similar structure, where we first construct a string based on the arguments, and then we send that string to the repeaters. Afterwards, we receive a reply, and then we pass that reply to some Julia type. And now we have a sequence of configuration steps. This is a really inefficient usage of our TCP stream, but luckily Julia's dispatch can help us with this. So as a first step, we can extract these common operations, such as constructing the command string itself or constructing the return type, into new functions that now take an additional argument, which is the function itself. And on its own, this doesn't change anything yet, but now we can actually write functions that take as input a vector of functions and the arguments, so a vector of commands to a repeater, and then we can execute them as a group or as a batch. So we can first actually send all the commands to the repeaters that we want to send before we start reading the replies and parsing them. And this allows us to use the TCP stream way more efficiently and save a lot of time. Julia also offers us a lot of options to make the transmission of the samples more consistent and high performing. We can, for example, use the producer-consumer pattern to really have a thread that's just dedicated to receiving samples from our cluster. And for this it groups the samples into chunks, and once it received the full chunk, it can pass it on into a channel which then can be used in a different thread. In this way we are able to achieve data rates of up to 750 megabits per second consistently. And when we read these individual chunks, because we're using TCP sockets, we don't need to read them one after the other from the red retires, but we can actually use Julia's asynchronous I/O to really read all of them essentially in parallel. And these are the ways that we can communicate and control the red retires. But as I mentioned, MPI measurements also needs to control a lot of other devices. And for that we have these two main data structures. We have a scanner, which is essentially just a dependency tree of devices which are loaded and configured from TOML files. And we have a protocol which are tasks that perform specific type of measurements given a scanner. And they are responsible for coordinating all these devices and spawning further tasks. And they also offer a channel for user interaction and control. And that gives us the following threading model, where we have a GUI that's responsible for display, user interaction, and logging. And this GUI can be exchanged for script or REPL. And this first component then spawns a protocol which performs some kind of measurement. And in doing so, it needs to spawn further tasks, such as a task dedicated on a thread for serial port communication, which can block and leave everything else unaffected. And it can also spawn, for example, the producer and consumer pattern. I'll leave with a more concrete example of this threading from a protocol where we need to perform hundreds of measurements. So I'll start with the measurement function itself. Here we open a channel and start the producer and the consumer on dedicated threads. And while the producer is still active, the protocol itself can react to user input. And after the producer finished, we know our signal has finished and we can shut down the red retires. And we do that again on a dedicated thread, because now we can already start preparing the next measurement. And you can see that here. And for the next measurement, we might need to move a robot, for example, so we spawn that on a dedicated serial port task. And then we still need to wait for the task from the previous measurement to finish, so that would be the consumer itself. And we need to wait for the previous producer to finish, because this shuts down our retires, and only after that has happened, we can start configuring the next measurement. And with this example, I'd like to thank you all for your attention.